Okay, so yeah, good evening everyone. I am Dilshit Dutta. Yeah, I am a research scholar at the Indian Institute of Science. So yeah, I am taking for today's problem solving session. Today we have the session number 11 for the course hydraulic engineering. It is being taught by Mohammed Saud Afzal. So yeah, let us get started. I hope I am audible. So yeah, in this session we will be covering the following topics. Basically, we will be covering topics based on computational fluid dynamics. So inside this broad topic, we will see what is the definition of CFD, how we apply CFD for solving problems related to fluid flow, and then we will see for the method of finite difference, where slightly in detail, where we will see what are different steps that are involved in the finite difference method. So in finite difference there are around six or seven steps. First, we have defined the geometry. Second, we have a discretization of the domain. Third, we have to specify the type of grid that we will be using for solving. Then we will start to specify the boundary conditions or the initial conditions that are required related to the fluid flow. And after that, we will be using a solver or the finite difference solving step, and finally we will get the answer. So for different types of PDs and different types of problem, like physical problem, we will be using different methods. So we see through one or two methods that are used for solving the most typical or most common fluid flow equations. And then we'll just see the basics of finite volume method. And okay, so before proceeding, we'll have a look at the fluid flow equations. So the first and the most important equation in fluid flow is the Navier-Stokes equation. So the Navier-Stokes equation is basically a fluid flow equation that is used for transport of linear momentum. So if we have incompressible flow, that is rho is equal to constant, in that case our continuity equation changes to, I am writing the equations in vector form. So this is the continuity equation. Our continuity equation changes to del dot V equal to 0, and linear momentum equation or the Navier-Stokes equation is given by this equation, that is for viscous flow. So on left hand side we will have rho dV by dt. This is the material derivative. Then minus of grad P plus rho g. This is the pressure force. Rho g is the body force, and mu del square V is the viscous force. A term due to the viscous force. So if we write this equation in Cartesian coordinates, we will get the following three equations. This is the continuity equation. This is the momentum in x. This is the momentum in y. And thirdly, we will have momentum in z. So this is just the expansion of the vector form. we've seen through these formulas before also. So now when we are dealing with turbulent flow, so we have to there is one more constraint, that there will be a fluctuation term. So whatever velocity that we have at a particular point or particular space, it can be separated into two parts. One is the mean velocity and other is the fluctuation velocity, the fluctuation term. So this method of decomposing velocity into velocity or the pressure terms into the mean velocity and the fluctuation term is called Reynolds decomposition. So so this is how our Reynolds decomposition is done. Where u equal to u bar plus u dash, where u bar is the mean velocity in the x direction and u dash is the fluctuation velocity in the x direction. Similarly for v, w, we have v equal to v bar plus v dash, w equal to w bar plus w dash, and lastly for pressure term, p is equal to p bar plus p dash. And there is one more thing, when you are dealing with this fluctuation terms, we should take care of some things. There are some conditions. One condition is that the average of the fluctuation term is always 0, because these values are extremely small and they will be fluctuating about the value 0. So the average will be always 0. And also the product of two fluctuation terms, and if we take the average, then also it is 0. And also when if you are taking derivative of these fluctuation terms, be it first derivative or a second derivative, it will be 0. These are for three properties, and the other three properties are this: if we are taking the product in two directions, that is ui, and then uj is u1 ui is velocity in ith direction, and uj is a velocity in j direction. So and ui dash we are taking, so it is a fluctuation terms, and if we take the product and the mean, we will get, and take the average of this fluctuation term, we will get 0. And then if we take the average twice of velocity ui dash of dash, then we will get only the mean. So the mean of the mean is equal to mean only. So these are the properties of Reynolds averaging. And then after this Reynolds averaging, we will get the continuity equation as this. So whatever continuity equation we had, so this is the continuity equation. So if we write u is equal to u bar plus u dash, v equals to v bar plus v dash, and w equals to w bar plus w dash, and then we take the Reynolds average. So if we take the Reynolds average, the fluctuation terms will go to 0. So only the average terms will be remaining, and the continuity equation will only have the average flow velocities in each direction. So this is the continuity equation after Reynolds decomposition and Reynolds averaging. Then we have the Navier-Stokes equation. So this is the Navier-Stokes equation for incompressible flow. We are neglecting the body force here. So it is like del, if you are taking in the ui direction, so del ui by del t plus del ui into uj by del xj. This is the convective acceleration. Then this is the 1 by rho del p by del x is the pressure gradient, force due to pressure, and this is the diffusion term. Del by del xj into 2 mu of dij, where dij is also the strain rate tensor, and we have seen before that what is a strain rate tensor. Strain rate tensor is given as half of del ui by del xj plus del uj by del xi. So we have these terms for Navier-Stokes equation, and then now if we take the average, if we take the Reynolds average and then do the Reynolds decomposition, we will get the Reynolds average Navier-Stokes equation. It is also called Reynolds average Navier-Stokes equation. So the Reynolds average Navier-Stokes equation is with this term where du bar by d of ui bar by dt, this is the material derivative of the average velocity, then we have the minus 1 by rho del p bar by del xi, where del p bar by del xi is the pressure gradient, and this is pressure gradient is only related to the average pressure, it is a mean pressure, and it is not related to the fluctuation pressure. And the final term we will have del by del xj of minus tau ij plus 2 mu of d ij bar. So in this equation, the term at tau ij, if we multiply with rho, it will give, first of all, tau ij is equals to average of ui dash into uj dash. So ui dash and uj dash are the two fluctuation velocities in ith direction and z directions, and the mean of the product of these two velocities. So, and if we multiply this term with rho, we call it the turbulent stress or the Reynolds stress. So what is the purpose of doing this averaging in turbulent flow? The purpose is to, like, if we are averaging this turbulent flow, we can try to solve it by a numerical differentiation or the numerical schemes that we do in CFD, that is computational fluid dynamics. So this makes our calculations and complexity a bit easier. So the final objective is to obtain the values of ui bar and p bar, that is pressure gradient and the velocities in each direction. So by taking the average, our job becomes slightly easier compared to if we take the overall velocity without this decomposition terms. But before solving the this Reynolds average Navier-Stokes equation, before that we have to solve for the Reynolds stress equation, that is we have to solve for this term. If we get if we solve for this term, then get an equation for this term and then solve it. After that, we can substitute this in the main Reynolds average equation, the Reynolds average Navier-Stokes equation, and get the final solution of velocity and the pressure gradient. So to solve this Reynolds stress equation, there is an equation for Reynolds stress, and this stress for the Reynolds stress equation is given by this. That derivation, like material derivative of the stress tensor, is equal to Pij, which is a product of Reynolds stress, then plus pi ij, where pi is a pressure strain correlation tension, and at minus of epsilon ij is a dissipation term, and finally rate of change del jik by del xk, which is the diffusive flux. And each of these terms is expanded here. This is the product of the Reynolds stress, the Reynolds stress multiplied by the pressure velocity gradient. So, and then pi ij is the pressure strain correlation, so it is p bar by rho into del ui dash by del xj plus del uj dash by del xi. And lastly, dissipation term is given by this 2 mu del uy dash by del xk and del uj dash by del x. Okay, so we are taking only the fluctuation velocities will only be coming in this equation, and finally we will have to take a average over the whole term after calculation. So this is if we substitute these terms and then we solve for the Reynolds stress equation, we will get a value for Reynolds stress, and then we will substitute that in the Reynolds average Navier-Stokes equation and get the solution for turbulent flow. So since it is solving for solving for turbulent flow is always a complicated process, and lot of softwares are trying to come up to solve for different conditions for turbulent flow, but even though we are still not very extremely close to reality, there is still lot of gap in solving for turbulent flow. Now we will see, like, okay, so this is we saw for the general Navier-Stokes equation and also the equation for turbulent flow. So there are some other types of equation that are related to fluid flow, like wave equation or the diffusion equation also, and we will see how we solve this using finite difference of finite volume methods. So these are called these methods come under the topic of computational fluid dynamics. So what is CFD? CFD is like it is used to get a solution of fluid flow equations numerically. So where we decompose or transform the differential equations into finite difference equations or finite volume equations, and after transferring them in numerically, we can try to get an approximate solution of the complex differential equations. So in CFD we can handle laminar flow with ease, since there is no extra equation for stress or no stress term, and there is no fluctuation component. And lastly, it replaces PDEs with discretized algebraic equations. So one of methods for solving before proceeding into methods, we will see the general procedure. How do we proceed for solving a differential equation? First, we have to define the geometry. Suppose for what geometry we are trying to get the equation. Suppose if we take flow in a pipe, so we would give the dimensions of the pipe. The circle is a circular pipe or a rectangular pipe, or if it is open channel, so it will be a width of the channel, the height of the channel, this kind of properties. So this will define the geometry of the we define a geometry where we want to get the fluid flow equations or the solution of the fluid flow equations. Then we will do the discretization of the domain. So in whatever region we want the solution or the velocity values or components, we will discretize that region into a fine mesh, and we will try to get the values of the velocities or the pressure at different nodal points in the mesh. So this is called discretization. First we define geometry, then we do the discretization. Then the third stage is called the solver stage. In this we solve the discretized equation of the flow. That is, once we have discretized the domain, we will get the equations in terms of, we will get algebraic equations. So these algebraic equations we need to solve it, and finally we have to solve it for different boundary conditions and initial conditions. So this we will have to specify while we are solving the problem. And lastly, we will have the processing stage. In the post processing, we will just see what is the error that we got, and we will try to minimize the error and get a near a very like proper or more accurate approximate solution. So I told about defining geometry, how we define the geometry. So that is like in computer we'd give the dimensions of the model for which we want to get the solution. Next, the second step is the discretization of the model. So in discretization of the model, we will develop a set of algebraic equations based on the discrete points in the flow that will be used in place of the PDEs. So to get the discretized equations, there are three main methods. One is the finite difference method, second is the finite element method, and third is the finite volume method. So we'll see this one by one. So in finite difference method, what do we do? In finite difference method, the flow field is like separated into a set of grid points, and the continuous functions are then approximated by discrete values of these functions at each of the grid points. So suppose if we have a flow field, so we have divided the flow fields into a lot of in a mesh, and we'll try to get the equations or try to write the equation in terms of the values at these grid points. So the I terms denotes the coordinate in terms of for the x, and the j terms denote the coordinates in terms of y. So next, in finite element and finite volume method, what do we do? In this methods, the flow field is broken into a smaller fluid elements. So for 2D domains, the cells or the fluid elements are areas, and for 3D domains, the cells are volumes. So then we write the differential equations in an appropriate form for each element, and the set of resulting algebraic equations are then solved numerically. So this is how the two methods. So now we talked about grid. In this we saw this is a in finite difference method, what we do, we write the equations. I will discretize the domain or the flow region into a finite mesh that will have grid points. So what is grid points? We can have a structured grid point, or we can have a unstructured grid point. So what is a structured grid point? So in structured grid, we will have a regular coherent and coherent structure to the mesh layer. So one example is the simple rectangular grid. So here all the cells are rectangular, or we can also have this kind of grid. So this is also one of the so if we have dividers region like this, you can see here also the regions, that is the cells are not rectangular, but it is slightly parallelogram or curved parallelogram. So in this case also there is a like definite structure to the grid. This is also a type of a structured grid. Then there is the unstructured grid. In unstructured grid, what is the pattern? So there is no symmetric pattern of the grid. So you can have this is unstructured grid. You can see all the cells in the grid are of different sizes, different patterns. They might be triangles, but the angle and the length and everything is varying for each of the element, each of the cell. So this is an unstructured grid. So how do we select a grid? So it will depend on the problem that we are trying to solve. Suppose if you are trying to solve for a very complicated geometry, like we are trying to solve for a bridge pier. So a bridge pier, it is like placed in the middle of a river. So in that case there will be a lot of turbulence around the pier, since the water is striking the pier at a very high velocity. in that case we cannot take a uniformly structured grid, since the values of the daily velocities in all the three directions and it is varying extremely rapidly. So we will have a unstructured grid near the pier for trying to solve the equations, trying to get the velocity components of the fluid flow near the bridge pier. So in this type of conditions we will have you will have to use unstructured grid. But when we are dealing with a flow through a pipe or flow in an open channel without any constraints, without any constraints in between, we will use the simple structured grid. That is, you can also use the rectangular grid or we can use the cylindrical grid. So this is the steps that are involved in solving a equation, that is a fluid flow equation using computational fluid dynamics. So we have one now. While solving in a solver stage, I told that we have to give the boundary conditions. So what are the types of boundary conditions? One boundary condition is the Dirichlet boundary condition. So in Dirichlet boundary condition, what we do? The velocity, we will have the velocity or the values of the velocity at the boundary. We will have the exact values of the velocity or the pressure components that you are solving. We will have the exact values of that. And second, we have the Neumann boundary condition, where we will have the values for the derivative of the velocities at the boundary. So this is a Neumann boundary condition. Now when we are dealing with wall, so when you are dealing with a flow through an open channel, so due to the flow will also have a wall. So at the wall there are two boundary conditions. One is the normal component of velocity at the wall is equal to 0, since there cannot be any flow component in the direction normal to the wall. And secondly, the no slip condition. So in no slip, what happens? The wall cannot move, so the tangential component of velocity at the wall will also be 0. So this is the wall boundary condition. And second, we have the inflow outflow boundary condition. So we'll give the values of incoming or outgoing fluid along the inlet or outlet face. So suppose we want to get the velocities of only in a part of a channel, and we know the suppose there is a constriction here. So we want to know the velocity, we want to get the velocity components or solve the fluid flow equations in this region. So we will have the velocities in the region where there is no with constriction. So we will give the boundary conditions in this region from the inlet, that is the inlet boundary condition that we already know from the flow before constriction. After constrictions, what happens to the flow? To see that, we will solve the fluid flow equations in this domain, and then via numerical scheme, and we'll get the solution for that. Okay, so this was about boundary conditions. Okay, now before proceeding into solving differential equations, first we should know what are the types of partial differential equations and how the methods for solving it varies. So one is the first type of partial differential equation is the Laplace equation. So the Laplace equation is given by del square f by del x square plus del square f by del y square is equal to 0. There is no time derivative in Laplace equation, so there is no propagation in time. Second is the diffusion equation. So it is del f by del t is equal to alpha del square f by del x square. where del f by, like, there is a propagation term in time and it is first derivative in time. And thirdly, there is the wave equation. So it is del square f by del t square is equal to c square into del square f by del x square. So it is second derivative in time and second derivative in space. So these three equations fall into three different categories. So how do we classify the partial differential equations? So this is a basic general equation of a PDE. A into fxx. What is fxx? Fxx is the del square f by del x square. Xy is equal to del square f by del x del y. Fyy is equal to del square f by del y square. And then dfx plus efy plus f into f equal to g. So first type is the elliptic partial differential equation. So elliptic partial differential equation is given by the condition this b square minus 4ac is less than 0, and the type of elliptic PDE is the Laplace equation. Since we have two terms, that is fxx and fyy in Laplace equation, so and in both a and c are greater than 0, therefore b square minus 4ac is less than 0. B square is always equal to 0. Next up we have the parabolic PDEs. In parabolic PDEs, what do we see? We have b square minus 4ac equal to 0, and the example of parabolic equation is the diffusion equation. So and thirdly, there is the hyperbolic PDE. Hyperbolic PDE is where b square minus 4ac is greater than 0, and the type of hyperbolic equation is the wave equation that we have seen here. So this was about the types of PDE. Next, based on the physical problems, type of physical problems, we have three types of physical problems. One is the equilibrium problems. Equilibrium problems are where we want a steady state solution of the problem, and the rate of change of the parameter with respect to time is 0. So we are solving these problems in a closed domain. So the one example of the equilibrium problem is the Laplace equation, like solving the Laplace equation in a closed domain. Then secondly, there is we have propagation problems. So the propagation problems are like where there is a time derivative. There is a time derivative and the solution will propagate in time, propagate forward in time. So we give a initial condition, and for the initial condition the solution will march the solution forward in time. So the examples of propagation equation are the diffusion equation or the wave equation. Since in both the two equations we have the solution is also have a term like where differentiation with respect to time. And third, it is called the eigen problems. So in this case the solution exists only for the particular values of parameter, and these particular or special values are called the eigen values. So for specific eigen values only we will have the solution. So now for Now we'll try to obtain the scheme for finite difference, how we will proceed for a solution in finite difference method. Suppose we all know the Taylor series approximation. Suppose if we have we know the values at a point I. In a field. So how we will get the values at the point I plus 1. So to get the values at the point I plus 1, which is separated, suppose at delta x or delta h, or it may be delta or any direction. We are taking C only for x direction. So in that case, the function value at I plus 1 can be approximated by Taylor series. So it is given as fx of I plus 1 is equal to fxi plus f dash xi into delta x by 1 factorial plus f double dash of xi into delta x square by 2 factorial plus up to n terms. This fn xi by delta x n by n factorial. Now we can approximate, we need not consider all the terms in the equation in the Taylor series, so we can approximate for the different orders. First we have the zeroth order approximation. In zeroth order approximation, what we do, so in zeroth order we assume that f of xi plus 1 is equal to f of xi. So we will be neglecting all the other terms in the Taylor series. So it is f of xi into delta x to the power 0. So this is why it is called a zeroth order, and the truncation error that we will be having will also be of the order 0. So this is the zeroth order approximation. If we have the solution curve for a curve of f like this is I and this is I plus 1. The actual value is here. We have assumed that f of x I plus 1 is equal to f of xi. So this value will be the error. So this is the first order approximation, zeroth order approximation. Now second is the first order approximation. In first order, what we do, we assume that f of xi plus 1 is equal to f of xi plus f dash xi into delta x by 1 factorial. We consider two terms in Taylor series, and the other terms comes in the error, and this truncation error will be of the order of delta x. And thirdly, there is a second order approximation. Here we will be considering three terms. There is still f double dash of xi into delta x square, and the other terms will become in the truncation error, and the truncation error will have the order of delta x square. So this is how we approximate the Taylor series, and now we will try to get the numerical differentiation scheme. So if we have 3 points in the fluid flow, or 3 points in the domain, one is I minus 1, it is I, and I plus 1. Then by forward difference du by dxi, that is the derivative of u with respect to x. This is the not a partial derivative, this is, we are talking about the ordinary derivative. So du by dxi, it can be approximated as the first derivative, and if we take only the first two terms in a Taylor series, we will get du by dxi is equal to u of I plus 1 minus u by delta x. So this is called the first order forward difference. Next up, we have the backward difference, where du by dxi is equal to ui minus 1 by delta x. So we will be taking the values at these 2 points in backward difference. It is at point, if you want calculating the derivative at point I, we will be taking the values at I and I minus 1. So du by dxi is equal to ui minus 1 by delta x plus of order of delta x. So this is also called the first order backward difference. And third up is the central difference. For central difference, first order because the order or error is of order of delta x. And the third central difference is we take the values at I plus 1 and I minus 1, and the separation between them is 2 delta x. So how do we obtain this? We obtain by this formula, ui plus 1 of minus of ui minus 1 by 2 delta x, and there will be the truncation error will be of the order of delta x squared. So in solving most of the problems in fluid flow, we will be also using central difference, since the order is of the second order, and second order means it is of the order of delta x squared. Since delta x is very small value, so delta x square will also be very small, so the error will be less in terms for a central difference scheme. Next, so this was we tried to obtain the finite difference schemes for the ordinary differential equation or ordinary derivatives. So if we have partial derivatives, then we will have a two-way stencil. This is called the stencil, like formation of these grids. We will have a two-way grid where I denotes the x and j denotes the y. Y oblique t. So for the first order forward difference for partial derivative is like del u by del x of at I comma j is ui plus 1 j minus of ui j by delta x plus the truncation error, that is of order delta x. And similarly, the first order backward difference will be del u by del x of I comma j equal to ui j minus ui minus 1 j by delta x plus truncation error. And thirdly, there is this second order central difference, for this is for x direction, that is del u by del x of I comma j is equal to u by I plus 1 j minus of ui minus 1 j by 2 delta x plus of truncation error. So this is the writing the partial derivative. So we now know how to write the equation, that is the differential terms in terms of terms in terms of algebraic form, that is in a finite difference discretized form. So if we take the diffusion equation, we can write it in terms of this. So the diffusion equation, how to do, we transform it like we take the central difference in space, and we take the forward difference in time. We can also take central difference in time, but taking central difference in from experiments and from modeling results, it has shown that taking central difference in time doesn't improve the result that much. So people have proceeded with the easier option, that is taking forward difference in time and then second central difference in space. So taking forward difference, so if we u depends on both I comma n, where I is the space term and n is time, related time. So ui n plus 1 minus ui n by delta t. So this is the forward difference in time and the central difference in space. So del square u by del x square, it can be written in this term. So the n will be staying constant, so only the I terms will be varying. see the second derivative, so it will be ui I plus 1n minus 2 ui n plus u I minus 1n by delta x square. So we have obtained the algebraic equation for the flow. We will write the equation for the whole domain, then we will give the boundary conditions, like at what values of, suppose at I equals to 0 or at n equals to 0, what is the values of u. So if n equal to 0, it designates a initial value problem, that is at initial time what is the value of u, and then if we give that, we can then proceed and for the solution and get a iterative equation, and then solve for the values of u at different u and n. So this is how we transform my equation into, we transform the diffusion equation into an algebraic or a discretized equation. Similarly, we can do it for wave equation also. For wave equation, it is del square u by we will take central difference in time and central difference in space. So this is how we transform the equation for central difference for both and with respect to time and with respect to x. Yes, and then we can proceed to solve the equation for the different grid points. Now while solving a equation, there are two things that we have to consider. First thing is the consistency. So what is consistency? Consistency is that we have discretized the domain into finite mesh, right? So as the mesh size tends to 0, or the mesh size is like we make it more final, then the analytical solution between the for the PD and the finite difference solution should tend to 0. This is called consistency. That is, if we are refining the mesh size, we are making the gap between the mesh nodes as smaller and smaller, then the solution, then the difference between the solution of the finite difference equation and the PDE will be equal to 0, and this is also equals to truncation error, that is limit truncation error tends to 0 as you refine the mesh. This is consistency. Our solution should always be consistent. And second is the convergence. The what convergence denotes is that the solution of the algebraic equation, that for approximating the PD, it is convergent if it approaches the exact solution of the PD for each value of the independent variable as the grid spacing tends to 0. So for convergent, it is if we have UIN so the solution that we obtained now as delta x and delta t tends to 0, the solution, like both the solution, that is the exact solution and the solution from the finite difference, they should be equal. they should be equal as both delta x and delta t times the 0. And thirdly, like when you are dealing with this partial differential equations, we are getting a grid spacing for both time and space. So when you are dealing with both the terms, they will get an error in both the time domain and also in the space domain. But what we should take care is that as we proceed forward in time or we proceed forward in the solution, the error, this is error in time and the error in space, both should decrease as we proceed or in the solution. That is, we refine the grid size and we get and we do more iterations. After that, the error should decrease. If the error doesn't decrease with the solution, then the solution is unstable. To obtain this stability condition, we should the grid spacing in the time and space direction is obtained by this formula. This is called von Neumann stability condition. Alpha delta t by delta x square is less than equals to half. If our mesh grid points meet this condition, then our solution is stable. Next is the finite volume method. What do we do in finite volume? Here the total solution, the solution domain is divided into smaller control volumes. And these control volumes can be rectangular or it can be simple quadrilateral. And secondly, so this is the solution is based on the cell valence equation and it is solved by integral approach. That is, we write the integral forms of differential equation and we solve those equations in the control volume. And more advantage of finite volume is that it is free from truncation errors. We can have a look at the cell structure of finite volume method. So this is delta x, this is delta y. So this is our simple rectangular cell or for a cell for a 2D flow. If you are taking the 2D solving for 2D flow, we will have we are considering a rectangular cell or rectangular control volume and we will writing the equations in this control volume and then solve. So this is the finite volume method. So this was all about the basics of the method. There are a lot of things that we need to see, but this is out of the scope of this course. So there are separate courses for CFD where you will learn all the methods that are used for solving these equations after discretizing. I just showed here how to discretize the equation, and after discretizing there are a lot of different methods. So one method is the Euler method. You can proceed with Euler, or you can proceed with Craig-Nicholson, leapfrog. There are a lot of methods like that, and each method has its own limitations and its own advantages. So all these methods you can learn if we study proper CFD course. So we'll look through some questions, some basic questions. So the first question is CFD provides results of continuous time varying results at discrete locations. No. Discrete points in space and time, yeah, we have discretized both in space and time. The second option is true. What are the dependent variables in the Navier-Stokes equation? The dependent variables are what? One is the pressure. Pressure is dependent. Then we have U, V, W, the velocities that we want. Then the density is also the dependent term, and the temperature. Temperature is dependent. Temperature we are considering because the stresses of the pressure will be a function of temperature. The pressure will come from the equation of state. So and it is dependent on the temperature. The equation state is dependent on temperature, so temperature is also a dependent variable in the Navier-Stokes equation. So next question is, the turbulence problems particularly depend on this term of Navier-Stokes equation, which is that term. So when you are dealing with the turbulence terms, we told that we have to take care of the diffusion term, that is Dij. So from Dij we only obtained this, the diffusion term, 2 mu into Dij. So this only leads to, while doing Reynolds averaging, this only leads to the Reynolds stress term and the average of the Dij term. This Reynolds stress is the most important term while solving for turbulent equation, turbulent flow. So the solution of the turbulent flow equation will depend on the Reynolds stress, and this Reynolds stress is the Reynolds stress term comes from the diffusion term. So it comes from the diffusion term. Also we can see the diffusion term has velocities perpendicular to flow, that is it will have terms del ui by del x j plus. So it is a rate of change of the velocity in a direction perpendicular to that velocity component. And in turbulent flow we know that if we have u velocity, then there we will have fluctuations in the direction of perpendicular to the component of the velocity. Similarly, this is v. There will be fluctuations of v in the direction perpendicular to the.
मुझे इंटरनेट से कनेक्ट करने में परेशानी हो रही है। शायद रूटर या एको डिवाइस में कोई समस्या है, इसलिए उन्हें रीस्टार्ट करें। दोनों का प्लग निकाल दें, फिर रूटर का प्लग वापस लगा दें। 30 सेकंड इंतजार करें। जब रूटर चालू हो जाए और इंटरनेट से कनेक्ट हो जाए, तब एको डिवाइस का प्लग वापस लगा दें।
Sorry for the interruption. So yeah, so diffusion terms have like both these terms, that is del u by del x, is the rate of change of the gradient, the velocity gradient in the direction perpendicular to that velocity component. And in turbulent flow we know that there will be fluctuations of the velocity in the direction perpendicular to its components. So this term is by intuition also, this term is the most important term in the solution of turbulent flow, Navier-Stokes equations for turbulent flow. Next question is, which method, what is the method used in CFD to solve partial differential equation? So variable separation, it is no, it is a analytical method. Method of characteristics is also analytical method. Change of variables also analytical method. We do discretization, that we discretize the domain and write the algebraic equations. Which of the following does not come under partial differential equations? In the Laplace equation, here we have seen the Laplace equation is a partial differential equation. Equations of motion doesn't come under partial differential equation. These are ordinary differential equation for the solid bodies. And 1D wave equation is the partial differential equation, and also heat equation is the partial differential equation. Heat equation is similar to the diffusion equation. Which of these methods is not a method of discretization? So, finite volume, yes, finite volume is a method of discretization. Finite difference is true. Spectral element, this is also a method of discretization. Gauss-Seidel method is not a method of discretization, it is a method of solving the discretized equations. I told that there are a lot of methods for solving discretized equations after discretizing. So one of these methods is the Gauss-Seidel method. It is not a method of discretization, it is a method of solving the discretized equation. While using finite element method, one has to approximate boundary conditions, integrals at grid faces, derivatives of grid points, and shape functions and weighting functions. So when you are using finite element method, what we do is that with the shape functions and weighting functions are approximated. So we haven't seen details of the finite element. So in finite element, what we do is we convert the equations of flow into a matrix form, and matrix for each of the parameters, and we give a weightage to each of the matrix, and based on the shape of the matrix and the weighting parameter that we give to the matrix, so based on that our solution will be varying, and we have to approximate these weighting and shape functions. Next is, what is Reynolds stress? Stress due to velocity fluctuations that we have seen. It is del Uy by del Xa. So these terms are from the Uy dash. So Uy dash fluctuation component of velocity, and how it is changing with a direction perpendicular to the direction of the mean velocity. So these terms are contribute to the Reynolds stress. So this velocity fluctuations only lead to a Reynolds stress term. Next, eddies in turbulent flow result in high diffusion coefficient. When there are eddies, there will be a exchange of momentum, and there will also be a exchange of mass. So the values of the diffusion coefficient, that is alpha, that we obtained. So the diffusion coefficient for, like, if you take the heat equation or take the mass equation or also the momentum equation, when you are taking the diffusion coefficient, it will be extremely high, because exchange of change of momentum, mass and heat. To close the Ray's equation, we need turbulence models. Ray's equation is the Reynolds average Navier-Stokes equation, and to solve that we need tau Aj, that is the Reynolds stress, and this Reynolds stress, it is solved by turbulence models. So we cannot directly solve the Reynolds average Navier-Stokes equation. It becomes extremely tedious and extremely complicated, and so it is very not feasible to solve the equation directly. So we need to have some turbulence models, and this, like, details of these models is out of the scope details of the models is out of the scope of the of this syllabus of this course. So here we do some approximations. Next is the multi-grid approach switches between dash and dash grids to meet the errors. So in multi-grid approach, what we do is that we switch between fine and coarse grid. So what happens is, like, when we are taking very small cells, that is for fine grids, there will be low frequency errors, and these create problem in the fine grids. Low frequency errors arise from the larger grids, and this cause problem in the fine grids. So this so in multi-grid approach, what we do sometimes switch between this type of grids, that is from coarse grid to the fine grid, so that we can reduce the error. And last is the upwind scheme is suitable for convection term. It is not suitable for diffusion, since diffusion is a non-directional phenomenon. And when you are talking about the upwind scheme, it will have a direction, and the convection term will always have a direction. So this is a scheme. So these types of scheme we have outside the scope of this syllabus also. So when you talk about upwind scheme, it is like there are a lot of other schemes like leapfrog scheme, Craig-Nicholson scheme, when you are dealing with finite difference methods. So for this, there are a lot of schemes, and all these schemes can be used to solve different types of solve the equations in different ways, based on the boundary conditions and the type of the solution of the equation. So yeah, this was about okay, this was about the CFD terms and the basic equations. So yeah, if you have any doubts you can ask me, else you can leave the meeting. Thing is that I don't set papers for the course. The questions will be, I think it will have will cover like I think MCQs, and also there will be some subjective questions also, I think, based on the concepts. And so be clear through the concepts that have been taught in the topics, and be like mostly this is hydraulics course, right? So for hydraulics I don't think there will be many questions from this CFD part, okay, from the this last part. There will be maximum number of questions from open channel flow, and then pipe flow, and this flow through weirs, and laminar flow, and turbulent flow. So these four topics are extremely important, so be clear with the concept. And yeah, so some questions will be, I think, fill in the blanks and this objective questions, and there will be some questions that you will have to solve. It will be numerical solutions. I won't be setting the paper, this is, I think, the general pattern of the paper. Okay, welcome. There are no more doubts, yeah, we can end this session. You can leave the meeting.